Observing a spacecraft land on a distant asteroid, scientists notice that the craft is falling at a rate of 5 meters per second. Okay. When it is 100 meters closer to the surface of the asteroid, the craft reports a speed of 8 meters per second. According to the data, what is the approximate gravitational acceleration on the asteroid? Okay, so basically the idea is we have some sort of rock, asteroid, and we have a lander craft, that is falling towards it. I'm going to assume it's falling. And the idea is it has some sort of, we're going to assume, did it say average? Approximate. Okay, so we're going to assume it has some sort of constant gravity. Now in reality, as things get closer together, the gravity will get stronger and it'll pull it faster and faster towards the asteroid. But we're going to assume it's constant. So, kind of like Earth, we're just trying to find a different gravity here. So this is going to be a kinematic equation. So we're going to assume the acceleration is some sort of constant. A equals A in this case. Velocity equals AT plus V naught. X equals 1/2 AT squared plus V naught T plus X naught. So we're given velocity, so I'm going to start by looking at this one, and then maybe that one as well, because we are given a distance, 100 meters. So, V final equals acceleration times time plus V initial. So I'm going to say that time equals V final minus V initial over acceleration. So I move the V naught over, divided by time. I'm not entirely sure that's going to help me yet, but I'm going to go with it. So then we have x final minus x initial equals 1/2 AT squared plus V naught T. So I just moved the x final over. And the reason I wanted to find that difference between x final and x initial is because we're given 100 meters closer. So this we'll know will be 100 meters. And let's see here. This, change color, 1/2 A, and then we have T, which I'm going to say is V final minus V naught squared divided by A squared, so that's T squared, plus V naught times V final minus V initial over A. Okay? So here, and then we have, so in this case we'll have one of the A's cancel, and we're left with 1 over A, because we'll just factor out the A, V final minus V initial squared plus V initial times V final minus V initial squared. No, not squared. And this will equal 100 meters. I'm going to call this delta X. Okay, so now rearranging things, because we know V final, we know V initial, we don't know acceleration, but we do know delta X. So rearranging this whole thing, we have A equals, supposed to be over 2 here. Over 2. There we go. That would have been disastrous if I'd forgotten that. V final minus V initial squared all over 2 plus V initial V final minus V initial. And then this whole thing will be divided by delta X. So I did a lot of rearranging there. I'm going to see if it works and then kind of explain my thought process if it works. If it doesn't work, I'll just pretend I never did it. So we have 8 and 5, V final, V initial, and 100 meters. So we have equals, this will be 8 minus 5, which will be 3. 3 squared is 9. 9 divided by 2 is 4.5. Plus V initial, which is 5. 5. Yep, starts at 5. 5 times 8 minus 5, which is 3. divided by 100. Okay? So we have 15 plus 4.5, which is 19.5, divided by 100, which gives us 0.195, and this will be in meters per second squared. Okay? Aha! You can have it as an answer. So, what happened with this one was I really had no idea what to do. It might have looked like I did. I assure you I did not. So the way I approach these is kind of take all the knowledge I have, all the data I have, throw it in a box, and then shake it up. After I'm done shaking it up, I see if it gave me something that I can use, something that's reliable and understandable. So in this case then, I was like, all right, I know I had a V initial, which is 5, a V final, which was 8, and so it's like, okay, I have some things I need for this equation, but I don't have time, and I'm looking specifically for the acceleration. So I was like, all right, on the other kinematic equation, I have time here and acceleration as well. So I have two equations and two unknowns, so I can use one to solve the other one. So I took this, solved for one of the unknowns. In this case, I solved for time. That way I'll be left with acceleration. Plugged it into my second one, kind of fiddled it around for a while, got lucky that all the numbers were kind of reasonable and I can kind of do them in my head. And from there, I just plugged through until I got an answer. So I would not memorize this process, be like, oh, okay, if I want to find acceleration, I do this. Think of more the process of, all right, I have two equations, I have two unknowns, so I can solve this, and then just methodically work your way through it. In this case, using substitution by substituting one variable, solving for one variable and substituting it into the next equation. And you just grind your way through it, try not to make mistakes, and after your long methodical journey, your trek, if you will, you get an answer, and hopefully it's correct. And if you do a good job, showing your work, you can go back and find your mistake if it's not one of the possible answers. So I hope that helped. Makes sense that this is a small number, smaller than Earth, since, it's generally assumed that asteroids are smaller than Earth. Okay, hope that helped. I will see you next time.